would be interested, please do so. Today, we're really glad to hear from Bill Boicourt. He's a widely recognized expert on the currents and winds of Chesapeake Bay. Bill has a long and distinguished career studying the circulation of Chesapeake Bay. You know, he's done some fantastic research. He's advised the state of Maryland on a lot of issues regarding the Bay. And he's been really a great person in educating our graduate students in the physics of estuaries. So Bill, thank you very much for speaking today. And the helm is yours.
Thank you, Mike. The title and the description of this webinar promises a lot in half an hour, but I just want to focus on three simple things. Not that simple, frankly, but three things. One, how do estuaries move? The Chesapeake Bay is the archetypical estuary where all basic physics were described back in the early 50s. I'd also like to look at how the Chesapeake Bay tides behave. I have a hint, they don't behave. And finally, we want to look at the role of the wind in driving the circulation, not just in messing up the tides, but actually in driving some pretty dramatic circulations that turned out to be far more important than we thought 10 years ago. So let's look at a map first of Chesapeake Bay. And the bay is really kind of atypical. It's a big estuary. It's 200 miles from where the Susquehanna River enters in the north to its mouth down here. The bay is described as a drowned river valley. You all know that during the last ice age, 20,000 years ago, the bay was just a river valley. Let me just run through the basic things I'm going to talk about in the bay. First of all, the basic estuarine circulation. We're going to talk about tides and these things called seiches. We're not really sure what a seiche, where that word came from. There's a rumor that it came from a Swiss dialect and it means slosh. That's where the seiches were first described on Lake Geneva. And then I'll talk about the wind circulation. Let's go back to this drowned river valley. 20,000 years ago, water level was 400 feet below what it is today. It was all in ice cap. Everything you see here pretty much was land. Even the continental shelf 100 miles out was land. And the rivers cut through the eastern shore of present Delmarva Peninsula. They went all over the place and ended out here. 10,000 years ago, the sea level began rising very quickly till about 5,000 years ago. Then it slowed down, drowning the river. So that leaves the basic geometry that defines the circulation. From about Chesapeake, from about Annapolis, where the Chesapeake Bay Bridge is, to right below the Potomac River entering here, there's a deep trough, the old Paleo Channel, that's about 100 feet deep. South of which, Rappahannock Shoals, here's the Rappahannock River, Rappahannock Shoals right here prevent wholesale entry of salt water and still get across there. And then there's a deep channel here. To describe the estuarine circulation, what I'm going to do is cut the Chesapeake Bay down its axis, and we're going to look at it sideways. The first view of it is going to be a simple laboratory experiment that my friends in the UK call a lock exchange experiments for their sea level canals. Here we have a very narrow tank. On the left-hand side is the fresh water, clear, pristine fresh water. On the right-hand side is dyed, very salty seawater. And there's a video here, and I've already started it, and I'm in the process of pulling out a dam between the two. And most of you can figure out what happens here. The heavy salt water is going to underrun. If you can't figure it out, there's a little hint along the bottom here. The fresh water is going to run across the heavier salt water. It doesn't occur that simply. We have what we love to call bores. There's a bore going here and a boring there. And let's watch. I'm going to pull it all the way out and make it move. Here's the bore going in the estuary and the surface bore going out. it slams up against the end here, and then you have these wonderful circulations, which we fluid mechanics get excited about, but we're not going to spend much time. But notice, you know, there's really not a lot of mixing going on here. Most of the blue you see in the upper layer is left over from the dye plating out on the side of the tank. There's very little mixing. On the whole, the ocean doesn't mix as much as we think it ought to. Now, this one-shot estuary here, if you add a river to this end, and you add take the barrier off to sea, you get a simple estuary, which we call a salt wedge. Salt wedge is sort of descriptive. There's this wedge of salt water that comes in along the bottom. The river enters this end over here. Light water flows seaward on top of the heavier water, just like in the lab experiment, except it's continuous. The boundary between the fresh water and the salt water is pretty sharp. These magenta lines indicate contours of salt content or salinity. This is a very sharp interface in salt wedges. An example of the salt wedge for our country is, the premier example is the Mississippi River. There's two good ones in Europe and that enter into the Mediterranean, the Ebro in Spain and the Rhone in France. The Hudson River and the Columbia River in the US are both salt wedge estuaries most of the time, but they have a lot of mixing, and we'll explain some how that happens. Now, the Chesapeake Bay.
Bill, we had a request that Bill, can you turn your volume up a little bit?
I'm not sure I can. Let me see if I can.
Yeah, maybe it's a participant. We've had a couple of comments. Thank you.
How's that?
Yeah, I could hear you fine. Most people said you're great. Thank you.
Okay. Well, we're back here at the salt wedge, and I'm claiming that the Chesapeake Bay is not a salt wedge. It's something really special. It's what we call a partially mixed estuary. What's going on here? Well, first of all, you have the river and the sea here, but what's different is you've got the lines of salinity are far more diffuse. By its title, you expect more mixing. If you move seaward, the particle gets saltier and saltier because it mixes with the salt water below it. Conversely, as the water comes in from the ocean, it mixes with the fresh water above. There's something really magical about partially mixed estuaries, and we're pretty good at describing why, but there's a lot of mysteries nonetheless. Here in the partially mixed estuary, you get something for nothing, or you appear to do. You put one river here, the Susquehanna, worth of flow in here. These arrows are supposed to indicate volume transport. So the volume gets bigger and bigger and bigger as you move toward the sea, such that by the time you discharge into the sea, the upper layer here can be 6 to 10 times larger than the Susquehanna flow as it enters the ocean. The underlying flow is 5 to 9 times bigger than the Susquehanna as it moves landward. So that magnification of a partially mixed estuary is remarkable, and it's special for these kinds of estuaries. Now, I want to show you how the actual currents are. This is transport here. So the way we usually measure it, we go out in the middle of the estuary and put a very big steel float underwater and then tie it by a taut wire cable to a heavy anchor and attach current meters. That's the way we used to do it in the old days. And the current meters would have various devices like a pinwheel that tell you how fast it's moving. For the last 30 years, we've been using pretty much acoustic techniques, sonars that sit on the bottom and look upward. They're much more accurate. They don't get run over by ships, and they give a lot of details on the vertical flow. So what on the next slide, I'm going to show you a profile of currents, but from this about mid-bay picture. But the sneaky part of it is I've averaged it over 2 months. So we're not seeing tides or anything else. We're just seeing the steady flow of the estuary. And here it is. Here's a profile from top to bottom, goes from 0 to 20 meters. That's about 100 feet. This is in the deep channel. It's in winter of 2010. And here's the profile where the flow to the right is in the ebb tidal direction toward the sea, and down below it's landward in the flood direction. And it's going about 15 centimeters a second, which is about 1/3 of a knot. And that doesn't seem like a lot. Remember, the tides are on the order of 1 knot, a little less than that. These flow can be easily dominated by the ebb and flow of the tides. But these are strong flows for oceanographic flows, not quite like the Gulf Stream, but they're strong flows, and they occur day in, day out. So a particle at mid estuary can get to the mouth 100 miles in about 10 to 15 days. So it's a strong flow. Now let's look at I mentioned the tides. Let's look at the tides. Think of this picture of a partially mixed estuary, not of a partially mixed estuary, but a small harbor, say Baltimore Harbor. And when the tide goes up outside the harbor, it flows in pretty quickly, and the surface level rises. Remember, the bay tides from top to bottom are only about 2 feet. Baltimore Harbor is only about 1.5 feet. The flow comes in, and then the high tide occurs, and everything stops. That's called high water slack. And then the tide starts going down, the flow gets stronger, and the flow gets out. The maximum flow out here occurs at mid-tide, and then when it gets to low tide, everything stops. So that's a typical harbor tide. We call it a standing wave. It's not what happens out in the main bay. Think now of this picture being in the main bay. It's 200 miles long. At the entrance to the bay, high tide shows up as a crest of what we call a tidal wave. Now that's not the same thing as a tsunami. It's the tidal wave propagating across the open ocean, generated by the sun and moon gravity acting on a rotating Earth. And it shows up at the mouth of the bay and starts moving in and propagates northward as a wave, as a crest of a wave, just like the kind of waves we see at the seashore when we go surfing. It moves landward at about 15 knots, and it takes about 14 hours to get the 200 miles from here to the head of the bay. Now, the period of the tide is 12.4 hours. So if it takes 14 hours to get to the crest, to the top of the bay, what happens? A new crest has already moved into the Chesapeake Bay. And so you actually have 2 high tides and in between a low tide at once. The maximum current occurs at the crest of the tide, the flood tide. So at high tide is a maximum current, in contrast to the harbor. And at low tide, it's maximum ebb. The relationship between tidal height and current can go all over the map. This is pretty well behaved in that sense, that as a progressive wave, it goes up the bay, but then it starts getting reflected and turning into harbor tides in the tributaries. That's why you need 2 sets of tide tables when you want to figure out the currents and the height. One for height is called tide tables, and one for currents called current tables. Now you do it all online, but in the old days you had to have 2 separate books. Now, I talked about the misbehaving Chesapeake Bay tides. Let's go to someplace simpler. Let's go to New York at the Battery, and I'm going to show you a tidal curve. This is tidal height from yesterday and today. I picked it down this morning. It goes from mean low water at 0 here to 6 feet here. It's a big tide up there compared to here. You see two curves. One is a blue curve. That's the forecast, predicted tide. That's done by figuring out where the sun and moon is, and they're easy to crank out by computer these days. And that's what we say that was going to happen. The actual tide yesterday and today are in the red curve. And there's two things you can see there. First of all, they don't agree in the sense that they're offset a bit. Well, the predicted tide doesn't take into account wind effects. There's some southerly winds here that are helping to raise the sea level off the mouth of the Hudson River. But also, the predicted tides don't include thermal expansion. When the spring comes and these hot days come, the water expands and gets a little higher. So that's the difference between these two tides. Now, I'm only showing you a couple days here, yesterday and today. Let's go look at the whole month in the same location at the Battery in New York. And you get a picture of the fortnightly variation of the tides. This is a beautiful tide record. You get the end of the spring tides over the left. You see the minimum range here in mid-June. These are the neap tides. And then growing to the spring tides. We recently had a full moon, still pretty big, and you get these beautiful spring tides just recently. I'll go on. I could go on about the details about this because there's wonderful mixed tides where a higher high tide and a lower high tide. There's some diurnal pictures in there too, but let's move on to Chesapeake Bay. Before we do, think about the kind of movements of water that you have to produce this beautiful tide. First of all, you got to move the water to fill and empty it. So if you put a current meter out in the Hudson River west of the Battery, and it would show a picture almost identical to this with a different scale. It'd be flow rather than tide. It's because if you have a well-behaved tide, you're going to have a well-behaved tidal current, and it's going to be beautiful like this. Now I want to take a current record from the upper level near the surface in the Chesapeake Bay in spring of, I guess, 97. I just happened to have this. And look how pretty a picture this is. And look at this mess here. What are we seeing here? This is about a month of record. Here's the time scale on the bottom. I've split it into a positive and negative. Positive is in the ebb or seaward direction. Negative is in the flood or landward direction. And the scale is 0 to 100 centimeters a second. That's 2 knots. And I want to draw your attention to the fainter picture, the squiggly line in the background. That's the actual current measurement near the surface. And you'll see, aha, for a while there's periods when it looks like a regular old tide, when you get flood and ebb and things are behaving quite well. That's a period when there's not much wind. I've also run a fancy mathematical filter through this to get rid of the tide, but let's not pay too much attention to it now. The point here is that it's not regular. It varies all over the map. There's some days, like here and here, when there's no ebb tide whatsoever. And there's no flood tide, sorry, and there's other days like here and here and here, where there's no flood tide at all. What's going on there? Let's go and look at the actual behavior of a wind hint driving the Chesapeake Bay. Here's a cartoon with 2 panels. The upper panel is sort of the beginning of applying a wind stress or wind down the axis of Chesapeake Bay, and the lower panel is sometime later. Let's focus on the upper one. The green arrow is the wind blowing down the bay. There's friction, so it couples to the surface of the water and drives the surface of the water pretty fast, upwards of 50, 60, 1 knot, sometimes 2 knots toward the mouth of the bay. That creates a deficit up here in the north end of the bay. And so it starts building this slope toward Norfolk, to the south end of the bay. at this later time, it takes about 9 hours for the slope to develop. That slope means that the water wants to come back. And what it does is slow down the upper layer flow seaward because it's still being blown by the wind, but it slowed it down. But down here in the lower layer where the friction and the influence of the wind is not very strong, it drives a pretty strong flow. So this is that classic two-layer lake circulation, but in this case, it's the estuary, and it's very dramatic. But here you blow the wind. 9 hours later, you get this well-developed slope. 18 to 24 hours later, you get this response in the lower layer. So it's really pretty complicated. Now, if you take the wind off, what happens to this slope? It's a wave. It bounces back, and it oscillates. This may be only 3 feet up here, up in the north end of the bay, 3 feet in Baltimore. Down below its regular level. In terms of the 2 foot tide, the 1.5 foot tide in Baltimore, that's pretty big. Well, if it sloshes back, then you got a 6 foot range. That's really big. It easily, with a strong wind, can dominate the regular tides. This sloshing, we call a quarter wave seiche. That's because this is only a quarter of it here. And it has a period that is determined as in Lake Geneva by the shape and length of the bay. And it turns out to be very close to 2 days. And it is the dominant, we call it the dominant subtidal motion, which means besides the tide, it's the strongest motion in Chesapeake Bay. Now let's go back to that messy current diagram and look at the black record here. And that's getting rid of the regular tides and only looking at the seiche driven by the wind. And you can see, you're all good time series analysts, you can see looking at the time record down below, these are pretty regular. When the wind blows, they crank up a 2-day oscillation in the bay. It's not always linked to each other because the wind can stop and start not in phase, but there are periods in here, especially in this area here, where you get almost resonance, where you blow like pumping a child's swing on a tree. You push the water out, and then you push the water. The wind switches around because of the low pressure system, pushes the water in. Another low pressure system hits, and you get this resonance phenomenon where you get strong landward and seaward flows and big ranges day to day in the tide in the northern bay. Because it's that seesaw action where this is the northern bay and this is Norfolk, you get most of the action in the height in the northern bay. Norfolk is sort of ho-hum. There's storm surges and stations down there, but they're not anywhere near as big in the northern bay. A lot more currents, because where's that? In order to fill and empty the northern bay, it has to go roaring down toward Norfolk and roaring back. So so if you have to predict the tide, or have to, like the so-called analysts for the stock market, figure out why it's the way it is today, look to yesterday and what the winds did. So you got that down. So yesterday it blew from the north and it blew the water down, the low, and all of a sudden today it's starting to come back and be higher than it was. So if people ask you, just talk about the winds yesterday and they look very confused. There is another sneaky thing going on here, and I want to use one particularly strong forcing, the famous nor'easter in March of 2018. Here's a tide record from Cambridge, Maryland, right near here where I'm speaking. In this case, the mean low water is here. This is 4 feet here and minus 2 feet here. Again, as in the Hudson River example I showed, blue is the predicted tide. That's the way that if the tides behaved in Chesapeake Bay, they would look like that. But the chartreuse is the actual tide, and it didn't behave that way. What's going on? Well, first of all, on the 1st of March, before the nor'easter hits, it's looked like in New York Harbor. It's behaving quite well. It's a little higher. perhaps a little wind there. But then the wind hits. And in Cambridge, we get the big rise initially. That's a local effect of wind being blown down the Choptank. That doesn't appear that strongly in the open bay. But then the whole upper bay drops to 2 feet below mean low water. The drop in from here to here is about 5 feet. And then really strong, it's blowing 60 knots of wind out on the continental shelf. Nor'easter is blowing, it's setting up big high seas and high storm surges on the coast. There was a lot of power outage and people getting killed. It was a bad storm. It goes into the fourth here and then stops, and then you see the rebound of the chartreuse line till it comes up above where it started, and then starts coming down a little bit. But then, that's the Seiche going back again, but then there's no wind, but it gets higher and higher. Maybe it's behind me there, unfortunately. It gets to be to the point where it's 6 feet above its low stand in only 3 days. And there's no wind. What's going on there? It's not this is beyond the 2-day bounce back of the Seiche. That's scary. What's going on? Let's look at the map and figure out. When that nor'easter hit, it blew the water out of the bay. But it also was blowing parallel to shore from Cape Cod to Cape Hatteras. It is the most effective way of setting up the water on the shelf because of the rotation of the earth. So all along the shelf, we got a 3-foot plus storm surge. So then it stops and the Chesapeake Bay starts surging back up to the north. But what happens to that 3-foot big wave that goes all the way back to Cape Hatteras? It propagates south along the coast because of the rotation of the earth as a wave and shows up at Chesapeake Bay at 3 feet above normal and propagates into the bay on top of the rebound. So here we have both a local effect and what we call remote forcing. So the bay is not alone. It doesn't behave by itself alone. We got to worry about the effect of wind on the continental shelf. Some of you, this is just a quick shot, might have seen the announcement in the Washington Post about the meteor tsunami that occurred 2 days ago. This is a tidal curve from Tolchester Beach in the Northern Bay. I'm a fan of meteor tsunamis, but let's skip that for now. It's not a particularly big one, but for tsunami nerds, it has a classic tsunami shape. It's only 1 foot high, come on. Anyway, let's move on. If you want to know more about that, you can. So we've got a basic quick picture of the 2-layer circulation in the estuary, how the wind can drive its own 2-layer circulation that either adds to or subtracts from or counters the 2-layer flow of the estuary. And we've seen how the wind can screw up the tides. Now, we, over the last 20 years, have started to learn in certain estuaries that have modest tides like Chesapeake Bay or Long Island Sound, that there's increasing evidence that it's not the tide that's providing the mixing for, or the main mixing for this partially mixed estuary. That's heretical because the tides, the bay's estuaries have been classified in oceanography by the how much mixing they occur, and it's all based on tides. But we got to the point where we wrote a proposal to the National Science Foundation saying we'd like to test the hypothesis that for the Chesapeake Bay and probably for Long Island Sound, that it's the wind that's more important than the tides. So we got funded, and it was a wonderful experiment. We got lots of money, $3 million to a 3-year program. We put out 23 moorings and a tower in the shipping lanes in Chesapeake Bay. I didn't sleep very well. We had 2 6-week field intervals and left the moorings out there for a year, a lot of them. Here's a picture of the big University of Delaware vessel we used. We needed for handling heavy gear, a lot of heavy gear, as well as handling our shipboard measurements in what we hope would be very windy conditions. We went out 6 weeks in March. You know, it comes in like a lion, goes out like a lamb. We went out for 6 weeks in October, November, the big cold air outbreaks. For the first 2 weeks, this is symbolic of the conditions we had. It was glassy calm. You know, this is a Murphy's Law. With all this work, $3 million, and there's no wind. And the same thing happened in the fall. The first 2 weeks of the experiment, no wind. But it turned out that was very, very lucky that it did, because on our very precise, highly instrumented tower, we found out something, that when the wind went away, the Chesapeake Bay reverted toward a salt wedge estuary, where the salt builds up, gets saltier and saltier in the lower layer, gets fresher and fresher as the water came down from the Susquehanna. The interface between the two, upper and lower layer, gets very sharp. And the tides, they're there all the time, were not strong enough to provide a partially mixed estuary. So we found out lots of other wonderful results, but that was the primary result that proved that our hypothesis was correct, that the Chesapeake Bay definitely is mixed by the wind. I'll stop there and entertain some questions.
Yeah. So Bill, thank you very much. We have a couple of questions. One person asked, you talked about north and south winds, but what if you have these winds from the east and west?
They do.
What does that do to the circulation?
They do affect the bay, and it doesn't take much of an angle but it's mostly the north and south wind that parallels the water that drives the flow, the strong flows. If you have wind across the bay, you can often get these circular motions in the bay, the reason why, another reason why cross bay motions of wind are not that effective, because you need a surface and what we call a fetch, a distance over which to get the momentum out of the wind and into the motion of the water. And the bay's narrow, and it takes a while for the waves to build up. So you don't couple the atmosphere with the ocean very strong with winds across the bay.
So another question, Bill, is during the sesh, does the rule still apply that maximum current occurs at maximum flood?
Yes, I had to think about that one. Yeah, that's correct. Because it is a tide, long wave that propagates exactly the same speed as the tide. It's determined by the depth of the water, and yes, it behaves exactly the same way.
Boy, these are great questions. This is going to get you. How much is Chesapeake Bay affected?
I want you to filter out the hard ones.
How much? Okay, well, I'm not going to do that. How much is Chesapeake Bay affected by the Gulf Stream?
What we thought 5 years ago, it wasn't. It turns out that because of the rotation of the Earth, the Gulf Stream, which is about 100 miles wide, has a slope. So here's my slope. Here's the inner wall of the Gulf Stream, and here's the Sargasso Sea toward Bermuda, and it slopes 3 feet in 100 miles. Now that doesn't seem like a lot, but that's huge in terms of ocean dynamics. If the Gulf Stream happens to move inshore, the continental shelf tides are going to be a little higher. And people discovered this in the National Ocean Service about 5 years ago. If we found out that short term can vary quite a bit with the Gulf Stream. It's not as strong as we originally thought, but it can affect it that much or this much, depending on where the Gulf Stream is. So it does affect it, but it's nothing like the wind.
When you get these rebounds of the tide after the wind, what kind of maximum currents could we expect?
Those currents, well, I won't go back, but the currents are typically on the same speed as the tides. So they're on the order of 40, sometimes 50 centimeters a second. Remember that part of that sloshing, there's also that two-layer thing going on at the same time, and you've got that superimposed. So at certain depths, it actually can be stronger than the tidal currents.
Oh, I really like this question.
Uh-oh.
Do tides affect fish and other animals in the bay?
Of course not. That's a throw off to Mike Roman, who's my favorite biologist on the bay.
Yeah, well, we've made studies. I mean, of particular effect are the small critters that don't swim very well. So that you know, for the larval oysters and larval fish and tiny little critters called plankton, which is Greek for wanderer, they really can't swim on their own. So they go where the tides push them. So they're the wanderers.
And the net
What
flow,
else?
the net flow of the wind is very important. We've shown that for larval transport of especially oysters, because they're planktonic for about 2 weeks or so. Is that right, Mike? And then the wind can carry them quite a distance in that time. The wind-driven currents. Now they
Yeah,
don't.
Bill and I spent a lot of time not in the bay but out of the bay and figuring out how the larval crabs, which spawn at the mouth of the bay, and their larvae are carried out, how ET gets home. So that's all controlled by tides and winds. Here's another one. Do tidal effects in the bay also affect tides up in the rivers?
The answer is yes, because the rivers communicate to the main bay, and that they set what we call the boundary condition. If the tide goes up at the mouth of the river, it propagates up the river. And we've done a lot of studies, and all these tributaries are wonderful in the bay. They end up being laboratories, and the Potomac is a particularly good example. When we had a Hurricane Sandy, we were watching the real-time tide gauges in the bay and advising people. And the northern, after the Sandy passed, the northern bay water levels that had gone up went down, and the southern bay water levels were going down. We thought everything was great, but lo and behold, that Sandy was so big that the big monster storm blew the strong winds down the Potomac, blew a storm surge across the bay and flooded Crisfield and the lower Nanticoke and Wicomico rivers. We weren't looking. The National Weather Service was looking, thank goodness, and predicted that our model said at Horn Point, Ming Lee's model said it would flood those areas, and sure enough it did. But we were looking at the northern and southern bay, thinking that's that simple. But now we're looking at the rivers and the response of the wind and the tidal height on those rivers while the storm comes.
That's great. Yeah, again, some good questions just keep coming in. How do you expect changing ocean temperatures to affect tides and stratification in the bay?
We project, Ming Lee and I are on the governor's task force to update the projected sea level rise in the bay every 5 years. And we project a rise to 2050. It's a little slightly smaller than our last projection, to be about 1.6 feet maximum over what it was in 2000. But beyond that, it's going to go considerably larger. And when the water gets deeper, the tidal wave moves faster. So it will change the speed where the tides go up the bay, but it also will change the period of the quarter wave seiche. It'll get shorter. It'll be shorter than 2 days. Temperature, the there's a lot of biological effects associated with temperature, but the primary thing with temperature will increase the height of the water yet a little more.
Okay. So this person asked, I have noticed that predicted slack tide lags a few minutes behind the high tide or low tide. For the sailor, current is often more important than height. Can you explain this lag?
Well, that lag is only that close in the harbor. Out in the bay, it's 6 hours apart between maximum current and maximum height. That's that progressive wave versus standing wave. And as the tide comes in the bay, why does it change from a progressive wave moving up the bay to a standing wave? It's because it gets reflection of the wave back from the head of the tributaries and the head of the bay and produces this standing wave that's where the height the slack water occurs at high tide. So it varies all over the bay, so that those actually you can work out from tidal predictions. But the wind tide, of course, you have to do it from yourself. And I was going to give this one plug here from this particular logo on the bottom. This is a logo of the Mid-Atlantic Regional Coastal Association Coastal Ocean Observing System, in which I've been participating for the last 15 years. We have 46 radars along the coast from Cape Cod to Cape Hatteras, measuring surface currents all the way to the edge of the continental shelf. We also have current meters in the Chesapeake Bay. This is the Chesapeake Bay Information Buoy System, this real-time reporting back, and real-time numerical models. All that is on the Oceans map that you can go around and look at real-time data, forecast. It's a wonderful set of data and forecast. And just go to Maracus, look it up, and Google it, and then look for Oceans map, and you'll see it. So what was the question, Mike?
Oh, no. Oh, let me see. I have to go back. Yes, I have noticed that predicted slack tide lags a few minutes behind the high tide or low tide. For the sailor, current is often more important than height of tide. Can you explain this lag?
Well, the lag in that particular case has to occur only where you've got that standing wave in a harbor. Again, if you're out in the bay, the timing between the lag is huge. I mean, it's more like 6 hours than instantaneous or a few minutes. So it depends on where you are, the relationship between the tidal height and the phase of the current.
Well, I want to be respectful of everyone's time. So I'm just going to have this one question, this last question, which I think is a fitting final question. It says, Bill, are you going to write a book documenting the discovery of how wind is more influential than tides?
We have about 6 or 7 papers out there about it, but writing a book, I'm not so sure, but we should write some more papers, and I'm not going to promise it, but we have some wonderful colleagues that help me on this project, and I'll get my whip out and make them write it.
Okay. All right, well, just a few following remarks. First of all, you could do a little clap for Bill. So today, we'll send out an email to you that will include the link to the seminar recording and a short question survey. So we'd appreciate your feedback, how we can improve these presentations. So, and also, if you have additional questions particular to Bill's seminar, please include those in your email. So we'll forward those to Bill so we could get back to you. I hope to see, see or hear you from the chat room next week when Cindy Palankis will talk about the use of living shorelines to reduce coastal erosion. So thank you all again for joining us, and I hope you and your families continue to be well. Thank you very much.
Thank you.